Thank you for the kind presentation. Yes, I'm Carolina Schillaci. I'm from Sapienza University of Rome. I will present to you on the fatigue behavior of high-strength welded joints through average strain energy density method. We will talk about welds. Why? Because they are one of the most used joining techniques despite their use, despite their lower fatigue resistance compared to the base material. And in this work, we studied different weld geometries under different boundary conditions, both in as welded and post-processing conditions. So what we did is we took data from literature, focusing on papers that were studying the fatigue resistance of welds. In particular, we took as data the geometries, the weather curves, and the boundary conditions. Then we did numerical simulation through numerical software called ANSYS APDL, applying the strain energy density method. And then at the end, we could compare different post-processing techniques in a unique master curve through the strain energy density method. Why did we use the average strain energy density method and we didn't use the nominal stress method, that is the one recommended by standards? Because this last one has some limitation related to the need of multiple master curves in function of the global geometry and the failure location. So talking a bit about the average strain energy density method, it is a local energetic approach whose main scope is the one of studying static and fatigue behavior of components. The base idea is that brittle fracture occurs when the energy density averaged on a control volume reaches a critical value that does not depend on the sharpness of the notch, but on the material. So here on the bottom part of the slide, I'm showing the control volume radius of the control volume for these sharp notches. And in this formula, for example, we can see that the control volume radius in case of fatigue investigation depends on the Poisson ratio, on the unnotched specimen fatigue limit, and on the threshold stress intensity factor. And even the values, for example, lambda1 depends on the notch opening angles, are the William eigenvalues. In some cases, the pre-stress coefficient is considered. It takes into account the load ratio effect. In particular, if the load ratio is lower than 0, the pre-stress coefficient is lower than 1. And if the load ratio is higher than 0, the pre-stress coefficient is higher than 1. And for as welded condition, a pre-stress coefficient equal to 1 is usually considered. So as I told you, we studied different geometries. We simulated in 2 different ways. So we made 2D simulations with notch opening angles that were varying from 110 and 160 degrees. And for longitudinal fillet weld, we have done 3D simulation with a notch opening angle of 135 degrees. So since we took data from literature, we had a lot of base materials because we considered only the base material properties, not the local ones. We had some issues with the control volume radius. So what we did is we considered a control volume radius for 2D simulations made of stainless steel, another control volume radius for 2D simulations made of structural steel, and a unique control volume radius for 3D simulation because it was the group with less data. So let's talk about as welded welds. First of all, I tell you that we didn't consider residual stresses. So we wanted to understand how to find the control volume radius, and we tried to minimize the scatter ratio of the set band. In fact, if we, in the upper part of the slides, we have graphs that are showing the scatteration function of the control volume radius. And in the bottom part of the slides, we have the graphs that are showing the average strain energy density in function of the number of cycles. So focusing on 3D simulations, the control volume radius that was minimizing the scatter ratio was 0.5 millimeters, but it's too big. It has not a physical sense. So reading papers of Lazzarin, we took the value 0.3 millimeters, and for this value, the scatter ratio is 2.15, and the results are shown below. For 2D simulation made of structural steel, the control volume radius that was minimizing the scatter ratio was 0.3 millimeters with a scatter ratio of 2.08, and the results are shown below. And for 2D simulation made of stainless steel, the control volume radius that was minimizing the scatter ratio was 0.2 millimeters with a scatter of 2.69, and the results are shown below. So here I'm summarizing all the as welded data. So each group, as I told you before, has its own control volume radius. So 3D simulation has a control volume radius of 0.3 millimeters. 2D simulation made of stainless steel has a control volume radius of 0.2 millimeters, and 2D simulation made of structural steel has a control volume radius of 0.3 millimeters. And for this overall graph, the scatter ratio is 3.2. And for all of this, the probability of survival has been considered the one of 19%. And this is the band of Lazzarin that usually for as welded B-sharp notches is the reference one. So as I told you, we consider different post-processing techniques, burr grinding, high-frequency mechanical impact, and ultrasonic impact treatment. As before, we tried to find the control volume radius, minimizing the scatter ratio. So talking about burr grinding, the one that was minimizing the control volume radius that was minimizing the scatter ratio was 0.25 millimeters with a scatter 2.77, but we can see that there is not a strong difference if we take a control volume radius of 0.3 millimeters. And the result for a control volume radius of 0.25 millimeters is shown below. Then for high frequency mechanical impact, as before, we took a control volume radius of 0.3 millimeters because the one that was minimizing the scatter ratio, that is 0.5 millimeters, has not a physical meaning. So we took 0.3, and the results are shown below. In this case, we considered a pre-stress coefficient different from 1. We had a log ratio of 0.1 and 0.5. And then for the ultrasonic impact treatment, the control volume radius that was minimizing the scatter ratio was 0.35 millimeters, but if we take a control volume radius of 0.3 millimeters, there is not a strong difference in the scatter ratio. So here I'm presenting two graphs. Both are average ray energy density in function of the number of cycles. And I'm showing the three post-processing techniques. The difference is that in the upper one, I'm showing these three post-processing techniques, each one with the control volume values that were minimizing the scatter ratio. And in the bottom one, they have a unique control volume radius of 0.3 millimeters because we have seen that there is not a strong difference between these three. And in the scatter ratio, in the first case is 3.69, and in the second case is 3.98. And the right part of the slide, I'm showing the value of the average ray energy density of each post-processing technique at 2 million of cycles. And in both cases, the ultrasonic impact treatment is the higher value, and burr grinding is the lower value, is showing the lower value. So at the end, we can say that the B-sharp notches were in agreement with Lazzarin band and Lazzarin values that are usually used as reference ones. And in both cases, burr grinding are where the values in the bottom part of the graph, and ultrasonic impact treatment, the one in the upper part. As for the developments, we could consider local material property, of course, residual stresses, and even other post-processing techniques like thick dressing and sandblasting. Thank you for your attention.